remainder theorem and factor theorem. So if we use synthetic division to divide, because you've already done these, we can go through them faster. What's my 0? Negative 1. So that's what would be on the outside. 1, negative 2, and a 0 and negative 4, so I'm missing that x. So then I have to drop down and start my multiplying and adding. So negative 1, negative 3, positive 3, positive 3, negative 3, and negative 7 becomes my remainder. So I get x squared minus 3x plus 3 is my quotient. If I substitute in negative 1, we get negative 1 cubed minus 2 times negative 1 squared minus 4. Negative 1 cubed is negative 1. Negative 1 squared is positive 1. Multiplied it by 2, I get negative 2 minus 4, and I get negative 7. If I look at B, and I look at my synthetic division, my 0 this time is 2. And I have 1, negative 2, and negative 5. Carry down, 2, 0, 0, and negative 5. So my remainder is negative 5. My quotient is x. Then if I substitute 2 into this equation, we have 2 squared minus 2 times 2 minus 5. So I get 4 minus 4 minus 5, which is negative 5. So what pattern are we noticing?
The remainder is equal to the product of, I don't know.
Well, what number have I put in here?
The 0.
The 0. So when I substitute the 0 into here, I get the remainder. So when p of x is divided by x plus 1, the remainder is equal to p of negative 1. And when I divide the polynomial by x minus 2, again, the remainder is equal to p of 2. This gives us a very important theorem called the remainder theorem. And really what the remainder theorem says is that when I take a polynomial function p of x and I divide it by this binomial x minus a, the remainder obtained would be the value of the polynomial when x is equal to a, or in other words, the remainder is equal to p of a. And that's an important concept to know, is the connection with that remainder theorem. The division algorithm, this is my proof. The division algorithm states that p of x equals the divisor times the quotient plus the remainder. If my divisor is x minus a, and then I get my quotient and my remainder, if I substitute a in for x, so I replace all of these a's with x's, I get a minus a, which is 0, times the quotient, which is still going to be 0, plus the remainder. So there's my proof as to why it works when I substitute this in. So use the remainder theorem to find the remainder when p of x equals 6x cubed minus 4x squared plus 8x plus 6 when I divide it by x plus 1. So if I have a divisor of x plus 1, what is my 0? Negative 1. So I substitute negative 1 into the equation. Negative 1 cubed is negative 1 times 6 is negative 6. Negative 1 squared is positive times the negative 4. 8 times negative 1 plus 6. So negative 6 minus 4 minus 8 plus 6 would give me negative 12. What would my 0 be for B? 1/2. So I want you to do the exact same thing, only substituting 1/2. into that function. Okay, so if I substitute 1/2 into this equation, I get 6 times 1/2 cubed minus 4 times 1/2 squared plus 8 times 1/2 plus 6. 1/2 cubed is what? 1/8. And when I multiply 1/8 by 6, I get 6/8, which reduces down to 3/4. 1/2 squared is
1/4.
And 1/4 times 4?
1.
So I get minus 1. Half of 8?
4.
Plus 6. So I have, this would give me negative 1/4. With the 10 would give me 9 3/4. Or 9.75. Or 39/40. So all 3 of those would be acceptable. So in class example number 2, it says find A if the remainder is 131 when P of x equals x to the power 2x to the power 4 minus x cubed minus ax plus 8 is divided by x minus 3, using synthetic division and using the remainder theorem. So if we use synthetic division, my 0 becomes 3, and then I have 2, negative 1, 0, negative a, and 8. And my remainder is 131. So with this one, I kind of work forwards and backwards. Bring the 2 down, I get 6. That would give me 5, 15, and then I get 45. And in order to get 131, what would I have to add to 8 to get 131? And what would I have to multiply by 3 to get 123? So I now have that negative a plus 45 has to equal 41. So then negative a equals negative 4. Or a equals negative 4. And then when I use the remainder theorem, I substitute in positive 3 into this equation. I know this part here looks like it should be positive a should equal positive 4, but when I look at the equation, it would have to be a negative. So the value of a itself is equal to 4, but when I put it into the equation, I get minus 4. Does that make more sense? So now when I use the remainder theorem, my 0 is 3, so I substitute 3 into the equation. And my remainder has to equal 131. So P of 3 equals 131. So 3 to the power of 4 is how much?
81.
And 81 times 2?
162.
3 to the power of 3? Minus 3a plus 8. So if I go 162 minus 27 plus 8, what do I get? So then if I subtract 143 on both sides, I get negative 12. And I get that a equals 4, which, again, my notation probably is not really the best that it could be on this side. I want you to realize that the value of a equals 4, but this minus sign would still be there. It would still be minus 4x. So if we look at class example number 3, we're going to use the remainder theorem again, but now we have two unknowns. So this creates a system of linear equations that we have to solve. And we have already done a question similar to this with linear equations. So find the coefficients of D and C in the following polynomial. If the remainder is negative 41 when I divide it by x plus 3, and it's 74 when I divide it by x minus 2. So if I look at my x plus 3, what would my 0 be? So I would put negative 3 into this equation. So P of negative 3 would equal 2 times negative 3 to the power of 4 plus D times negative 3 cubed minus C times negative 3 squared plus 5 times negative 3 minus 8. And the remainder, when I substitute in negative 3, is negative 41. So P of negative 3 equals negative 41. And then negative 3 cubed is 81 times 2 is 162 minus 27D. Minus 9C minus 15 minus 8. So if I go 162 minus 15 minus 8, what do I get? Okay, so negative 41 equals 139 minus 27D minus 9C. Because my coefficients on these two variables are negative, I'm going to pull them over to the other side to make them positive. So that I get a positive 9C, a positive 27D, and then I'm going to move the 41 to the other side to make it positive. And what is 139 plus 41? Okay. What can you tell me about the numbers 9, 27, and 180?
They're all divisible by 9.
So let's divide them all by 9. 9 divided by 9 would be 27 divided by 9, and 180 divided by 9.
20.
If I do this now, it's just going to make for a simplified equation when I combine it with the other one. So now I do the same thing. I find out P of 2. So 2 times 2 to the power of 4 plus D times 2 cubed minus C times 2 squared plus 5 times 2 minus 8. So I'm going to give you a moment, and I want you to simplify that equation, and then we'll look at the two equations together. So if I go through and I start completing this, my remainder is 74, so P of 2 is 74. 2 to the power of 4 is 16, so I get 32 plus 8D minus 4C plus 10 minus 8. 32, 42 would be 34 plus 8D minus 4C. If I subtract 34 on each side, I get this. And what can I do to all three of these numbers? Factor out of 4. I can divide them all by 4. So now if I took this equation and wrote it below this one, could I do something with the two equations to eliminate a variable? Pardon? Add them together. If I add them together, the C's are going to cancel out. I'll get 5D equals 30. So 1D would equal 6. So now that I know the value of D, I can find out the value of C by plugging it into either formula. 3 plus, or sorry, not 3. C plus 3 times 6 equals 20. C plus 18 equals 20. So what would C equal? 2. So that's one example or one way that we can use the remainder theorem. The other way, which is the way that we're most concerned of, because our ultimate goal in this chapter is to be able to factor polynomials. When I factor a polynomial, I can find out information about that polynomial that will allow me to graph it without relying on technology. To factor it, we're going to use this remainder theorem. Because if something is a factor, so how do I know that 5 is a factor of 20? When I divide it, I get 4 with no remainder. So when I ask you to factor a quadratic, you're finding two factors that divide evenly into that quadratic formula. When I ask you to factor a polynomial, you'll be doing the same thing. So the remainder theorem can help us, because in the remainder theorem, if x minus 2 was a factor of this polynomial, what would my remainder be? If something is a factor, what's the remainder when I divide it?
There is no remainder.
There is no remainder, so the remainder would be 0. The binomial x minus a is a factor of the polynomial if and only if p of a equals 0. Or in other words, the remainder equals 0. That's what we found out when we did the synthetic and the long division. We can use the remainder theorem because it's shorter. I don't need as much space, even with the synthetic division. I don't necessarily need the same amount of space. So to show that x minus 4 is a factor of the following polynomial using both synthetic division and the factor theorem. If I use synthetic division, 4 goes to the outside, 1, 2, and negative 24. So when I drop the 1 down, multiply by 4, 4 and 2 equals, multiplied by 4, add them together, there's my remainder 0. Or I can substitute it in. P of 4 would equal 4 squared plus 2 times 4 minus 24. So 4 squared is 16. 2 times 4? 8. Which equals 24. And when I subtract 24, I still get 0. Okay? In class example number 5, we're kind of working a little bit backwards. If p of 3 equals 0, that means 3 is a 0 of the polynomial. So if I go to write this as a factor, I have that x would be equal to 3. So my factor would then be, how would I write this as a linear factor? X minus 3. With my p of negative 2/3, that means that I would have x equals negative 2/3. So what would my factor be? X plus 2. I want to get rid of this, or I want to move it to the other side. So I'm going to start off by multiplying both sides by 3. and then add the 2. If P of 5 is equal to P of negative 2, which is equal to 0, what would be the second degree factor of this polynomial? So, if P of 5 equals 0, what's my factor going to be? X minus 5. If P of negative 2 equals 0, what would my factor be? X plus 2. So my polynomial function I get by multiplying factors together. So then P of x is going to be equal to x minus 5 times x plus 2. And there could be other factors, but those are 2 of the factors I know for now. If I want to write it as a second degree factor, I multiply this out. So x times x gives me x squared. I have a 2x and a negative 5x, which is negative 3x. And then 5 times 2 gives me negative 10. So in class example number 7, you're given 2 factors, and you're asked to use the factor theorem, which is just a subset of the remainder theorem, to tell me which of those 2 are an actual factor. I'm going to give you a couple minutes to do that. Tell me which of these 2 are a factor of that polynomial. Okay, so if I look at the first factor, x plus 2, my 0 would be negative 2. So 4 times negative 2 cubed minus 16 times 2 squared minus, negative 2 squared, minus negative 2 plus 4. So negative 8, negative 32, this is a positive 4, so I get another negative 32, positive 2 plus 4, so I get negative 64 plus 6, negative 58. Yes or no? Or did I do it wrong?
Isn't 16 times 4 64?
Oh, yeah. Negative 32 minus 64. So then I get negative 90. So then the 2x, so is this a factor? No. Because I actually have a remainder. The 2x minus 1, my 0 would be 1/2. So I get 4 times 1/2 cubed minus 16 times 1/2 squared minus 1/2 plus 4. So 1/2 cubed is 1/8 times 4 is 1/2. 1/2 squared is a quarter, and a quarter times 16 is negative 4. So negative 1/2 plus 4 minus 1/2 plus 4 equals 0. Is this a factor? Yes. Okay. Class example number 8 says, show that 1 is a root of the equation and find the other roots. From last year when we were doing quadratics, what was the connection between roots and factors? They were the same. The root of an equation was the factor of the function. And then the x-intercepts, all of those were interconnected. So to show that 1 is a root of the equation, I show that it equals 0. So if I do that, so 1 cubed is 1, 1 squared is 1 times 9, so I get minus 9 plus 20 minus 12. This does equal 0. So if this equals 0, it means that it is a root of the equation. So now I can use my synthetic division to divide, because that means that this is also a factor. So if 1 is a root, x minus 1 would be the factor. So if I do my synthetic division, 1, negative 9, 20, and negative 12. 1 times 1 is 1, negative 8, positive 12. I get a quadratic, so I get this polynomial, which would be x squared minus 8x plus 12 is another factor. So this is also a factor. Can you factor this quadratic? Can you give me two numbers that multiply to 12 and add to negative 6? Or sorry, add to negative 8. So negative 6 and negative 2. So then my equation, x cubed minus 9x squared plus 20x minus 12 equals the product of the factors. X minus 1 was the first factor I found, and then I found this quadratic, which I then factored again. And now I have my factors. So the other roots, what's the root for x minus 6? 6. And the root for x minus 2? 2. And if I know that my roots are 1, 2, and 6, if I drew a graph of this, what would I know about that graph? Yeah, it'd have the 3 x-intercepts at 1, 2, and 6, which is really important, and that's what we're going to work on next week, is factoring these polynomials and then looking at the graphs of these polynomials. So your questions